Right, plate boundaries and their landforms. So those of you who did GCSE hopefully already know this, but just a quick recap. So we have three different types of plate boundaries. We have constructive plate boundaries where the two plates move apart. We have destructive plate boundaries where the plates move together. And we have conservative boundaries where the two plates move past each other, or one plate is moving one way very fast and another plate next to it is moving the same direction but much slower. Both of these two, whether they're sliding past each other like that or going the same direction, just one is faster, will still create friction between the two plates, and that's the thing that will create the various disasters. So with plates that are moving apart, these constructive plate margins, the two plates move apart. That allows this area of weakness for mantle material to come through, which forms volcanoes, usually underwater. This whole process of the magma squeezing through very small gaps will create friction, and therefore you will get earthquakes. Also, if you look at this from above, so if you take a mid-ocean ridge and your two plates are moving apart, sadly the whole plate doesn't actually move at the same rate. So the plate here that's moving westwards and the plate here that's moving eastwards might move at a slightly different speed to further down the plate. So this might be moving much, much faster away from each other. What this then causes is kind of like staggered lines all across your mid-ocean ridge, so that this part can move independently from this part, but they're still part of the same plate, they're still going the same direction, just slightly different speeds. So again, this kind of brings us down to this little section here, doesn't it? Because this part of the plate is moving that way slower than this part, is going to create friction along here. Hence, we get earthquakes as well as volcanoes along these boundaries. The good way to see this is if you go onto Google Earth, go to the middle of the Atlantic Ocean and look at the mid-Atlantic ridge, you will notice, you'll see lines that cross the ridge like that. And it's essentially looking at the different parts of the plate moving at slightly different speeds. Let me get rid of that. So along these boundaries, we get volcanoes and we also get earthquakes. Where we have two plates moving towards each other, one of them will always go underneath the other one. Well, almost always, but we'll get onto that later on. This brings us back to some theoretical ideas about different types of plate. So there are kind of three scenarios. In fact, let me get rid of that at the top so I can draw some stuff. So if we have an oceanic plate meeting an oceanic plate, one of them is going to go underneath each other, but they're both a similar density. But one of them will always be a bit older and therefore a bit denser because it's had the weight of the ocean pushing down on top of it for a little bit longer. So the older, denser one will always be the one that subducts or goes underneath. So the posh word for that is subducts. If we have an oceanic plate and a continental plate meeting, hopefully you can answer this question already. Which one is the most dense? Oceanic is the most dense. It's got the weight of the water pushing down on it, compacting it. So it will always be the oceanic one that subducts underneath the continental one, which is far more buoyant and floaty. We get a weird situation though, where we get two continental plates meeting. Both continental plates will both have a similar density and neither one of them will want to go beneath the other one. So what happens rather than one subducting is they actually just push together and they crumple. So what you'll end up with is crumpled plates in the middle, which forms a very distinct landform, which we're going to talk about later. Now you'll notice that we've got plates in two of these scenarios going underneath other plates. What then happens at depth, this plate will melt. The melted material becomes less dense and hot and will rise. When it rises to the surface, it will form a volcano. So therefore, at these destructive boundaries, we will get volcanoes because we've got friction, because you've got one plate trying to squeeze beneath another plate. We will also get a bit of a friction, which is going to give us earthquakes, and we'll talk more about that in a second. So for these ones, we get volcanoes and earthquakes, as well as the constructive ones where we get volcanoes and earthquakes. The only one that's different is this last one, which are conservative margins, where we've got two plates sliding past each other. there is there's no plate going beneath another plate here, so we're not going to get any formation of molten rock that is melted. And equally, there is no gap opening up in the plates, therefore there's no weak area for magma to seep through. So the only thing we will get here is earthquakes. There are no volcanoes on conservative margins. That's a very quick, brief run through of what you'd done at GCSE. Let's get on to the A-level stuff. So first of all, where we get constructive plates, we're now not going to call them constructive. We're now going to call them, yeah. Quickly, because I'm doing a video.
Light from the bear is not on.
Okay, you will have to wait a minute and I'll come put it on, okay? Good girl. Sorry. So divergent plate boundaries. They used to be called constructive at GCSE, but try and use divergent instead. So two plates moving apart. We get two different landforms where we have these divergent plate boundaries. One of them is a mid-ocean ridge, which we talked about when we did paleomagnetism. The other one is something called a rift valley, but we'll start off with mid-ocean ridges and we'll go from there. So wherever we have two oceanic plates moving away from each other, we're going to have, as we said before, a gap or an area of weakness kind of opening up, which will just be some sort of small crack. Where we've got upwelling of mantle material, because this is where our convection current kind of upwells and then pulls the two plates apart, we've got a source of magma that is going to work its way through these tiny little gaps and erupt on the surface of these two oceanic plates as underwater volcanoes. This in itself, because you'll have lots and lots of them, will sort of create a bit of a ridge. At the same time, remember, this area down here is going to be hot. So this little section here is going to be sort of superheated. When you heat things, especially solids, it causes them to expand. So what also happens with a mid-ocean ridge is not only do you have volcanoes on the top, but I can't really draw it again now, is you'll actually have that bit expand. So you'll naturally create a ridge, and on top of that ridge, there will then be volcanoes too. Hence, we call it a mid-ocean ridge or an MOR. And these are usually, but mid-ocean ridges are always underneath the ocean, and divergent plate boundaries in general are usually underneath the ocean. So we never normally see these. They're just kind of these underwater seamounts that we can vaguely see from space on Google Earth, and that's about it. But there are a couple of instances where these actually do poke out the surface of the sea as very large islands. And one example of that is Iceland. Now that's got something called a hotspot underneath it too. And we're going to do hotspots as another landform. This will make more sense in a second. Essentially, a hotspot gives an extra big source of magma. So these volcanoes, would eventually become big enough to then start to surface above the ocean, forming these little islands. Best example of that is Iceland, but there are very, very few of them along mid-ocean ridges, just that one. So that's mid-ocean ridges done. Rift valleys, oh god, these are really blooming difficult to draw. So rift valleys are wherever you get two continental plates ripping apart. So let me just draw some land on there and some land on there. Okay, there's our two continental plates moving apart. So as you can imagine, we've still got these convection currents pulling these two plates apart from underneath. But we don't just get what we do under the ocean, where you've opened up a bit of a gap and you've got volcanic material coming through, creating new land, etc., etc. And what happens when you move these two big slabs of rock apart is you actually get collapse in the centre. So rather than magma filling the gap, you create a valley on the surface, hence we've got a bit of a valley there. And the material that once was there kind of falls into this valley. Now, I've drawn this and it looks really, really tiny, but actually these valleys can be tens of kilometres across. The best example of a rift valley is the East African Rift. If you go and have a look on Google Earth now, go down to East Africa, and what you'll see is some big, large lakes. And essentially that is where the Rift Valley is just filled with water, and so rainwater has fallen in over millions of years and accumulated. And that's essentially the start of a new ocean. So what will eventually happen is this land will rip apart so much water will accumulate in the middle. That big lake, and again, if you have a look at East Africa, you can see where that big lake is eventually going to join to the sea when it rips apart enough. And eventually it will form an ocean. So we said that most divergent boundaries occur underneath an ocean. The only exception is where a new ocean is starting to form, and we call that a rift valley. Again, you'll need to have a look at some theoretical diagrams of what they look like, because there are different features in here where the rift actually sort of pulls apart and bits fall in. There's these things called horsts, so I'll let you do a bit of research to find out what they are and to draw them onto a little diagram. But that's basically how rift valleys form. So that's our divergent boundaries done. So convergent boundaries, oh god, we get a whole load of different landforms wherever we get our two plates coming together. I've kind of mentioned already, we used to call these at GCSE destructive. I'd like you to get in the habit of calling these convergent boundaries. They're converging, they're coming together, if that makes sense. And we get three different main landforms here. So where we get two plates coming together, we said already, one of them will end up subducting unless we end up getting two continental plates meet. So usually an oceanic plate will go underneath a continental plate or an oceanic plate. Where that happens, we get a very distinctive landform. I'll do this with my hands and attempt to make this look fairly logical. So two plates are meeting. One of them starts to subduct underneath the other one. Now, if you imagine these are two massive slabs of rock, there's going to be a lot of friction where my nail's currently meeting my finger. And what actually happens is, rather than it just kind of rubbing and creating earthquakes, it actually pulls back part of the plate that it's trying to descend under, making a bit of a V shape. Now, that V shape, if that happens under the water, will create a massively deep ocean trench. And there are some really, really deep ones. Have a little look at something called the Mariana Trench. If you have a little look and Google or go on YouTube and type in Mariana Trench, James Cameron, and he actually made a one-man submarine and went down to the deepest ocean trench. It's deeper than Mount Everest is high. It's colossally deep, and there's very little that lives at the bottom there, but he did find some cool things. So it's just simply the friction caused by the descending plate pulls the plate descending under backwards, creating this V-shaped trench. So what you'll get, if this is the ocean here, is this little section here, you'll get a very deep V-shaped trench. That's very easy as that. The problem is with this is that, imagine you're bringing that plate back into this V shape. At some point, the frictional forces aren't going to hold that plate there, and eventually that plate will flick upwards. What that's then going to do is create a very, very large earthquake, loads of seismic waves rippling through the land and the ocean. What that will also do is create a tsunami. So tsunamis are created when the water above a plate is displaced. So this flicking motion will cause the water column above it to shoot upwards. That water column, as it shoots upwards, will get to a point where it loses energy and will then collapse down. That will create big waves that will then travel outwards, and as you saw from the Boxing Day tsunami, will create some horrendous situations for anyone nearby. So deep ocean trenches, you'll also get earthquakes, and as well as earthquakes, you could possibly get tsunamis. As I've already mentioned, this plate over here, as it descends, is going to get very hot and melt, creating magma, and that magma will then rise to the surface and create volcanoes over here somewhere, which brings us on to the next little section. So that's deep ocean trenches. The next one is island arcs. Oh, that's lovely. I've got a few more minutes, darling, and then I'll come and help you, okay? So where we get the situation, this one only happens when we've got oceanic and oceanic. So that was deep sea trenches. In addition, we have these things called island arcs. So when the plate descends, melts, the magma rises to the surface, creates these underwater volcanoes. Eventually these underwater volcanoes can become big enough to then come out the surface of the ocean, and they'll create, obviously, islands above them, volcanic islands. At the moment, it doesn't look much like an arc. Darling, you need to be quiet, please. Joby, do you want to be loud? You're going in the other room. But if you look at this from a bird's eye view, you can then start to see where the whole arc thing comes. Again, you'll need to go onto Google Earth to have a look at where this happens. Find an example of where an oceanic plate meets an oceanic plate. Around the Pacific plate in particular would be a good place. And have a little look along the edge of that plate. You should see a nice kind of arc of islands, if you like. There's a fantastic one if you have a little look between Russia and Canada, where the two land masses kind of almost meet. In between there's a beautiful arc of islands. I can't remember what they're called now because it's been can't remember. Don't know why. So let's do this from a bird's eye view. So you've got, this is an oceanic plate over here, this is an oceanic plate over here, and this oceanic plate is descending beneath this one. So what you're going to have, if you could have a look under the ocean, is you're going to get a deep sea trench here. And this always happens a little bit away from the actual boundary itself. So remember I drew that diagram before, and your volcanoes don't appear in the middle, your volcanoes appear kind of a little bit over here. So what you'll find a little bit over here is you'll find some islands popping up, some little volcanic islands, and you'll end up getting this kind of arc shape. As I said, if you go onto Google Earth, you can see a few examples of that. Then fold mountains. So our final landform that we get along convergent boundaries are fold mountains. And unfortunately for you, there are two types of them. We get young fold mountains and we get old fold mountains. The old fold mountains are the easiest ones. We've already talked about these. Where we get two continental land masses coming together. Neither one of them subducts, so one won't go beneath the other because they're a similar density, and instead they will simply crumple up and they'll form these mountains. They're called old because continental crust is older than oceanic crust, hence the actual rock here will be really, really old rock. Best example of this is when India crashed into southern Asia. It created the Himalayan Mountains, the highest and oldest mountain range in the entire world, and they did exactly this. They crumpled. I have got this here, which kind of I can use as a bit of an example. So if this was kind of the centre, and these are our two continental plates moving towards each other, essentially what happens, again, kind of as they push towards each other, they crumple and they rise, and you'll end up getting these old fold mountains. So it happens exactly like that, end up getting these folded mountains inside. So the old ones are really easy to explain. Younger ones, not so. So young fold mountains happen when you get a continental plate, attempt to draw this one, meeting an oceanic plate. As I said before, your oceanic plate is always going to subduct below your continental one because it's going to be denser because it's got the weight of the water compressing it. So your continental crust is always going to be the one that's more buoyant and doesn't go anywhere. But when this happens, if you imagine along the bottom of the sea, you've got loads and loads of material, sedimentary materials, bits of sand, bits of dead fish and crustaceans and shells and all sorts of other stuff. And that loose material won't go down with the solid rock. It won't be subducted, so something happens to it. And essentially, as the oceanic plate is subducting, all this material here gets, over hundreds of thousands of years, squashed upwards. So you get a larger and a larger and a larger accumulation of sediment here. And imagine this has happened over millions and millions of years. It gets squashed and squashed and squashed by more and more material pushing into it until it actually forms these folded mountain chains along your continental landmass. And again, if you were to have a look at them inside, they'd have all these lovely folded layers of rock and stuff. And it's just simply sedimentary material from the bottom of the seabed that has been squashed and compressed onto land and creates these very, very large mountain ridges. And the Rockies and the Andes in the two Americas are good examples of young fold mountains. So old Himalayas, young Rockies and the Andes. Jodie, if you're going to be loud, darling, you need to go in the other room, okay? Jodie, turn it off. Other one. Go in the other room, please, until I've finished. But the last bit, sorry, she's having a right strop now. And the last one is just to explain hotspots, which are our last feature. So these don't come with a plate boundary. Again, we did cover these briefly at GCSE. So we have these weird anomalies. If you have a little look at maps that show where volcanoes and earthquakes happen, most volcanoes and earthquakes will happen if we've got some plates. Most of them will happen along a plate boundary, so we'll mostly get volcanoes along here and we'll get these earthquakes along here too. But we do get some oddities, so sometimes we'll get earthquakes in the middle of a plate and sometimes we'll get volcanoes in the middle of a plate. And we are less certain about how the earthquakes actually occur in the middle of a plate. We believe it's kind of resettling or the tension from the plate being subducted somewhere else. But volcanoes, we very much know what is going on with these, and we call them hotspots because, as the name suggests, they are spots of extra heating. So if we were to look underneath, we've said so far that we have these convection currents going on underneath in the mantle. But we also know it's not quite that simple. We don't have these lovely little circulations of magma going round and round and round. We also have these random areas of extra heating, a bit like we know we have sunspots and solar flares on the sun. We have these extra hot and extra cold little parts. So we know that in some places in the mantle, we have these extra areas of heating. So from the core way down here, we believe we have what we call mantle plumes of hot mantle material that just continually come up in the same place. They're completely independent, we believe, to these convection currents that are going round and round. And we know these hotspots do not move. They are permanently in the same position. So that means you could have your plate boundary over there and your plate boundary over there, and in the middle of your plate you'd end up getting some sort of volcano. These give us some really kind of cool features. So we know that these plates are still moving. So this plate is moving in this direction, for example. Just because this plume of mantle materials coming up in the same place doesn't mean that the plate's going to stay still. So we're not always going to have a volcano here. So what will eventually happen, if this plate is moving in this direction, this volcano is going to move over here somewhere, and another volcano will end up in the place where it used to be. So we end up getting this little chain of islands. Now, don't confuse these with island arcs. Island arcs occur around plate boundaries parallel to a plate boundary. Hotspot chains of islands will happen randomly in the middle of a plate somewhere, and they're usually in a fairly straight line. So what ends up happening is you'll get a little chain of islands. So remember, obviously, the islands, so you'll see in between them. And you will have one that is active and is still being supplied by that mantle plume, and then all the ones that used to be above the mantle plume that have now moved away from the mantle plume will be not active anymore. They'll be completely extinct. They're never ever, unless they happen to go over another hotspot, be active again. So they're completely dead volcanoes. Notice I've drawn them. As they get further away, they get smaller. This is for a few reasons. So one, this is hot things expand, so this is going to be much hotter and bigger, and as they go away from the heat source, they're going to contract as they cool. But also remember, we have a lot of overlaps between different units. These are going to be eroded by the sea and by weathering, so they're going to be weathered and get smaller as they go further away. In fact, to the point where often away from that, you'll get really tiny ones that don't even poke above the surface of the sea anymore. So you'll get a whole line of islands and then what we call sea mounts going off into the distance. Best example of this is Hawaii. Again, those of you who did this at GCSE might remember I got you to go onto Google Earth and have a little look at Hawaii. If you have a look at Hawaii itself and then zoom out, you'll see the other Hawaiian islands. It used to be where Hawaii is, above that hotspot, above that mantle plume. And as time has gone on, obviously they've moved further away and they've become extinct. If you then zoom further out, you'll see the line of seamounts. And in fact, you can even see with Hawaii where the plate is obviously at some point in geological history moved direction, because you actually get this line of seamounts going one direction and all of a sudden it shifts northwards. So I highly recommend going and having a look on Google Earth and having a look for that Hawaiian island chain and also the seamount chain as well, because it's really quite cool. You could do a little experiment at home if you wanted to as well, and those of you who are in my GCSE class will probably remember this very well. What I did, I'll try and mimic it here, is I had like a mesh, so imagine this was some sort of mesh, and I had a can of squirty foam underneath the mesh, and I sprayed the squirty cream, or you can use shaving foam or something, and what ended up happening is you'd have like a little, well, obviously tower of cream on one side of the mesh, on the top of the mesh, and then I moved I kept the can of whipped cream in a still position, and I moved the mesh across, and then I sprayed the can again, and you'd end up getting another little mound of cream. Do the same thing and you end up with little mounds going away from your mantle plume. And again, it just explains in a nice 3D way how hotspots and the island chains that you get with hotspots actually form. I think that's it. We've done divergent, convergent. We haven't talked too much about the conservative margins where they're going next to each other, mainly because it is simply the frictional forces that are held up between those two moving plates will suddenly shift when the frictional forces aren't enough to hold those two plates still anymore, and you'll just get an earthquake. And there's nothing more complex than that. You need to talk about the build-up of tension, build-up of friction, then eventual release of that friction. There are no other landforms associated with them, and the only thing you tend to get is some sort of offsetting. So if you go there where you've actually got sort of the plate boundary, say some people, again you can Google those pictures of this, if some people have built a fence that happens to go across the plate boundary, over time what happens is one part of the fence will end up shifting further away than this one, so you'll end up with a fence that gets right around like that, and you'll have a step in it, and you can see roads that have a kink in where the plate boundaries moved and stuff like that as well, which is quite cool. But there's nothing more complex to them. So that is it. You need to sketch each different landform and add a paragraph to explain how each one forms. Hopefully the video's been useful. You might want to find some better diagrams, but entirely up to you. I've got a little activity that I'll give you next session, which kind of consolidates all this onto one kind of worksheet, and you can fill in the worksheet and label the different landforms. So I'll kind of assess you on it. But if you can upload your documents, that will be fantastic. See you later.